So, last class we did we showed that the laws of thermodynamics are consistent with the definition of entropy that we got from our statistical counting. So I would. So this is a recipe for what you have to do for the canonical ensemble. Sorry, the micro canonical ensemble. So first you calculate gamma e from the h of pq. Then find entropy using the Boltzmann relation. Then find E in terms of S and V. Then you can find the various thermodynamic quantities E equal to del U del S constant and E del U del V S constant S. And other free energies can be found as the Helmholtz free energy is U minus Ts. G is equal to U minus Ts plus G, and so on. To study any equilibrium behavior later, um, use thermodynamics. So there is another definition of entropy called, uh, which is valid for any probability distribution. So you can define entropy in this fashion. So this is the probability of each of the various microstates, and you sum over pi log pi, and you get a definition of entropy. This is consistent with our microcanonical ensemble. As you can see, S is for the pi for microcanonical is basically 1 by gamma. So Kb is if you compute this. So there will be a gamma e number of terms in the sum because there are gamma e microstates, and so each of them are the same value 1 by gamma e ln gamma e because the probability is constant for all the microstates. And if you sum over that, you get this gamma e by gamma e, and you basically get back the same definition of entropy, Kb ln gamma e. So you can use this definition of entropy for any probability distribution. And so what does this imply? So this S is like a measure of the disorder in the system. So if your probability distribution is sharply peaked at one probability or one value, suppose it's like this. This is some microstate. Uh, if your probability is 1 for this and 0 for everything else, that means you have complete information about the system. And if you substitute that, all the other terms is 0 and log of pi, one of them would be 1. So that would be 0. So you would get S equal to 0. So when you have complete information about the system, you would have S equal to 0. And if we maximize S for different pi, we would get all pi equal to constant. So all pi equal to constant is the state value of maximum disorder. So you all of them are equally likely, and yeah, sum of pi should be one, right? Because it's probability distribution. Yeah. Will be that part, that pi would be zero, right? So you can mix. So you can maximize s equal to minus kb ln pi times pi with the constant that sum over pi equal to 1. So you know the method of Lagrange multipliers? Okay. So what you basically do is when you normally maximize, you set this equal to 0, right? If your pi are variables, and when you normally maximize a function s, which is a function of pi, you take this as 0. But here you have a constant that sum over pi is 1. So subject to this constant, if you want to maximize s, you just have to do this. Your lambda times the sum. Constant. So you take s and take some undetermined lambda and multiply by the constant equation, and you maximize this function with respect to pi. And if you do that, you can so this is called the method of Lagrange multipliers. And if you do that, you can get the maximum value of s subject to this constant that pi is sum over pi is 1. So if you do that, so del s del pi is basically minus kb this is the derivative of s, and let's call this s lambda. The whole thing is s lambda, and the derivative of this with respect to pi is s lambda. So make this equal to 0. So you can put a kb term. So you get ln pi plus 1 minus lambda equal to 0. How is that kb term? I mean, you can put a kb term. It's just a constant, right? So you get pi equal to e power 1 minus lambda, and you get this lambda from the constant, sum over pi is equal to 1. So all of pi, so pi does not depend on I. So for all I, you get a constant quantity. So you get sum over pi is equal to basically 1 by from I. So what I've shown you is when your all the probabilities are constant, pi is constant, your s is maximized. So so that is a state of maximum disorder in the system, and so that's when all of it is equally likely. So, yes. Let's see. classical ideal gas. So we know its Hamiltonian is just basically the sum of all the kinetic energies because there's no potential energy in the system. So I want to yeah. So for this we first calculate sigma e, which is 1 by h power 3n. So yeah, so since your Hamiltonian does not depend on Qi, you can do this integration over Qi. It would just give you the oh, I, it would just give you the volume power n. So because dq1 to if you integrate over the all possible values of q, you get the volume velocity. So gamma of e gives v bar n h bar. So you see that this integral is like finding the volume of a sphere in this 3n dimensional p space. So let's call the radius as uh, root 2 m. So you can also write this as sum over pi square is equal to uh, less than equal to root 2 m whole square. So this is like finding the volume of the sphere in this 3n dimensional p space whose radius is root 2m. So there is a formula for finding uh, the volume of an n-dimensional sphere with radius r. Obviously, this will be proportional to r power n, and let's call the constant as Cn. And you can show that this constant turns out to be um, where this is the gamma function. And for integers, you can gamma turns out to be gamma n plus 1 is equal to n factorial. So we can substitute in this in our expression. So this is the volume of the our 3n dimensional sphere with r. Now our r is root 2 me. So so finally our sigma e turns out to be this. So I've taken this h power 3n over here. Okay, so this is a Planck's constant. How did it appear here? Yeah, so basically there is a Heisenberg's uncertainty principle, you know that, right? So in that you have del x times delta p of the order h. So H cube is the minimum volume your two atoms can come together. So that is the separation between. So your atoms can't come closer than that H cube volume because of this uncertainty principle. So there is some amount of because our classical picture is not adequate. We need to. So this is the minimum accessible volume, and for counting the number of states, you find the volume divided by the minimum accessible volume.
In the previous lecture, we just wrote sigma of E is equal to
Yes.
the integral. Why didn't we write X then?
You could have written it there, but so I was trying to do that for, I mean, a general any system. Uh, so in that you would have that system would have probably have a minimum accessible volume, and you can find the number of states by dividing with that quantity. So this basically
Doesn't gamma give the number of states?
gamma is like the volume, right? It's a continuous volume, and if you divide by this, you get the number of states. Because you can think of one atom like one atom can't access like two atoms can't access in the same volume at a single time. So if you divide your space as volumes of h cube, h cube, h cube, uh, you can put like one atom at one h cube and so on, and you can count it that.
No, my question was, uh, shouldn't that be instead of sigma gamma? Like gamma gives the number of points accessible, right?
Okay, so I had shown you that entropy you can calculate from sigma also.
Okay.
So I'm just calculating. And from this you get log of Cn to be n by 2 log pi from the numerator. And this is basically n by 2 factorial. If your n is large, it's close to it. It doesn't matter, it's even or odd. So this, and I'm using the Stirling approximation, which will give you n by 2 log n by 2 plus. So if I can take a log of this expression and multiply by kb. And if you do some manipulation, you will basically get this by substituting 3n over there. You will basically get this. And this is like s in terms of e and b. So you've got s in terms of e and b, and you can invert this relation to get e in terms of s and b, and so that comes out to be
Yeah. Is that kb 3 by 2 n kb?
yes. So this is the expression of E in terms of S and V, and you can find T from this. T is del S, sorry, del T del S at constant V, which if you do a derivative, you will basically uh, get this guy out. And the remaining part is basically E itself. So you'll get this. And so from this you get E is equal to 3 by 2 n kb. And this was the same relation we got from the equipartition theorem, if you remember. And for pressure, you can find del U, del E, del X. This comes out to 2U by 3B. And if you substitute E from here to here, you basically get this as n kT by B. So this is your equation of state, the ideal gas law. So you have got the equation of state of ideal gas from this counting thing.
You calculated sigma E using an assumption that uncertainty say h by cube के अंदर में है. So
Okay.
this gives you an approximate order of the number of states, right?
Yeah.
This won't be the actual number of states. You can't say this is the actual number of states.
Yeah, but because you're taking a log, it doesn't matter. So from this, then there's so there is some paradox which arises from this, which is called the Gibbs paradox. So we just derived the expression for the entropy, which is S equals NQ log. Where U is basically 3 by 2 kT and S naught is equal to 3 by 2. So this is basically the entropy per unit volume. If you see the expression, you can so if you substitute E to be kT, sorry, 3 and kT by 2 and remove the volume, you get this. And consider there are two gases with two different gases with N1 and N2 number of particles, and they are separated by non-permeable partition. And suppose you suddenly remove the partition, and the temperature doesn't change. So each of the system increases its initially it was in V1 and this is in V2. So each of the gas will go from occupying V1. This will go from occupying V1 volume initially to total volume N2 will go from V2 initially to total volume V. So both of them increases volume, and so there will be an increase in entropy because of this. So that increase in entropy uh, would be basically this is the increase in total entropy N1 K log V by V1. If you see the V term inside and if you subtract, you will get this V by V1. And this is the increase in entropy for the second graph. So this is the normal mixing entropy in gases, and this is the correct thermodynamic relation if you have seen it. But the problem comes when you suppose when N1 and N2 are both the same gas. So if these are both the same gases, removing the partition doesn't change anything. You just have a single gas and it's spread out all over the body. There should be no increase in entropy. But this equation predicts an increase in entropy. So this is a paradox. Um, because there is no term which kind of makes the increase in entropy zero when you just remove the partition. It doesn't matter what gas you have in these two, you always have an increase in entropy. So there should be something which causes this change in entropy to be zero when these two are the same gas. So Gibbs basically showed that when you put a term of 1 by n factorial to the counting, you basically don't get this increase in entropy for the same gas. And this he put it like without any logic. I mean, he just put it so that it does not give the it gives a change in entropy to be zero. So let's see. So you just evaluate gamma e. While evaluating gamma e, you divide by 1 factorial. So basically, in the entropy equation, you would have a subtraction of this term. So this term would be subtracted from the this entropy, and if you do that, you get this. This is the Stirling approximation. Yeah, tell me what should I do?
From the paradox is that entropy should be zero, but it's not.
Right.
Then he's putting n factorial.
Yeah, he's dividing whatever gamma e we found out. He's just dividing that by n factorial.
Okay. After that.
So when you're calculating s, you would take a log of gamma e. Right? So that means there would be a minus of log of n factorial. And in the Stirling approximation, log of n factorial is this.
Oh.
And so you just subtract this from the entropy. So whatever entropy we got there, we're just subtracting this term. So when you do that, you get this. So if you see, there was a 3 by 2 nkb. This n made it 5 by 3, so it will be 5 by 2 nkb. And I think everything kind of and you see this v by it was v initially, it becomes v by n, and So now if you find the new equation of state or your so if you invert this relation, you basically get this. This is S naught. And if you find your new so your del E del S remains same T. So this division by n factorial basically does not change your equation of state and does not change your definition of temperature. So you can so this is saying that you will not you're not going in the wrong direction. This
Does not have any physical sign.
it is the entropy when temperature is zero. Is it?
Why did you divide the one by?
I'll tell you later. After some time. So if you see the now if you have that same situation of n1 and n2 and you have basically this v by n. For different gases you would have the same increase in entropy because you would again have s to be log these guys will cancel out and it will be v by v1 and v by v2. Now, if you have um, uh, if you have the if you have a different if you have the same gas on both sides, your V by N remains the same both initially and finally. In this case, your V by N was changing from V1 by N to V2 by N, but if you have the same gas, your V by N remains the same because the density is remaining the same even if you remove the partition. So in this case, you can see that your delta S would be zero if both gases are the same. Is this thing clear? So in this case, we were comparing only the V's. Uh, this is same for all both, but here we are comparing the V by N's. And the V by N remains same even if you remove the partition for both sides. And if you subtract the final versus initial entropy, you will get it to be zero in if both sides are same. So now why do we absurdly like divide the gamma e by 1 by n factorial? So this basically lies has a quantum reason. So when we counted our states, we basically considered all our particles as distinguishable, which means that if you had one arrangement of particles and you swapped two particles, it would be considered a different arrangement. But clearly, our gas, like if we say that we have one kind of gas, uh, this this interchanging of um, uh, particles would not make any difference. Should not make any difference. So these are identical particles. So, but classically, these are all these are distinguishable. Only in quantum mechanically you can say these are identical, and changing these just they don't basically change the wave function of the system. Uh, and so classically we were considering all these arrangements as different, but uh, this we were basically double counting all these for a single arrangement. Suppose all these so you could permute the particles in n factorial ways, and all these were being double counted. So if you divide by the n factorial, you would get what you get for identical number of all the particles being identical. And since now in if you have two different kinds of gases, now these two particles are distinguishable, and that gives an entropy increase. But when you have the same kind of gas, that time the particles are identical and you won't see any entropy increase. So let's see one more type of system. So suppose you have total n particles, and you can and they are arranged in such a way that they have either zero energy or they have some energy epsilon. So you can number the particles 1 to n, and these are distinguishable particles. One can have energy 0 or e, two can have energy 0 or e, and so on. So what is the microstate of the system? So the microstate of the system would be the set of all n1, n2 to n, where this can be 0 or 1. This, all these can be 0 or 1. So when n1 is 0, it would mean that the first particle is in the 0 energy state. When n1 is 1, it would mean that the first particle is in epsilon energy state, and so on for all the particles. So, what is the Hamiltonian of the system? So so your Hamiltonian of the system would be basically whenever ni is 1, it would contribute an energy epsilon to the Hamiltonian. So it would be the sum over ni. And when ni is 0, basically it does not contribute to the Hamiltonian, and you can see from the sum. And let's call this number to be n1. So n1 is basically the number of particles in the epsilon energy level, and n0 is the number of particles in the uh, zero energy level. So what is the probability distribution? So the probability of one of these configuration of states would be basically 1 by where this is the total energy of the system, which is E. This is the total energy of the system, and this is the total number of particles in the system. And this sigma is omega is basically the number of ways you can arrange these particles in the system, such that your total energy is E and number of particles is N. So, so how many ways do you think can we arrange uh, uh, these N1 particles in energy E and N naught particles in energy 0?
N1.
Right. So basically your sigma En turns out to be n factorial by n1 factorial, right? And your Kb is sorry, S is basically Kb uh, log of omega. So, which if you apply the Stirling approximation, you get this. If you apply your Stirling approximation, you can basically show that it comes out to be this. And we know that N1 is equal to epsilon N1 is equal to E. So I can write N1 as E by epsilon. And I'll just substitute that over here. So S E as a function of N gives. So we have um, S in terms of E and N. And we can calculate 1 by T from this. So if you find this, you get this. So finally you get 1 by T as minus AB by epsilon and log of E by N epsilon. And if you invert this, you get E as a function of temperature, which is N. Okay, sure. Okay, sure. So if we plot E as a function of T, we get this kind of graph. So at T equal to 0, it is 0, and at T tends to infinity, it goes to n. However, if your energy is greater than n epsilon by 2, you see from this temperature expression that you get a negative quantity. So n epsilon minus something greater than n epsilon by 2 makes this greater than 1. And so you have a negative sign over here. So you get T to be less than, so T as a negative quantity. And that's quite counterintuitive, right? So T is negative for E greater than N. So why did this happen? So while you're counting states, when your energy is greater than n epsilon by 2, basically you have more number of particles. N1 is greater than N0. So as you keep increasing N1, your number of permutation or number of states or multiplicity keeps decreasing as you increase N. So as you're increasing energy, basically you're decreasing the number of the multiplicity of the system. So that means your entropy is basically decreasing as you're increasing energy. So this leads to something called negative temperatures, and these negative temperatures are hotter than positive temperatures. So your T goes to infinity, that time it goes to n epsilon by 2, and if your energy is increased more, your T turns negative. So if you keep a system with negative temperature in contact with a system with positive temperature, the negative temperature has higher energy, so it will lose energy to the system with positive temperature. So in that sense, basically your negative temperatures are hotter than your positive temperature. So you can also calculate the probability that N1 is equal to probability of N1 basically. So this is the probability that particle 1 is in the in either of the zero state or first state, independent of the other particles. So for this, what do? You would sum over all the other probabilities, sum over all the configurations of the other particles, and P of Ni. But what is this? So if your particle 1 is in the epsilon energy state, your total energy is basically E minus n1 epsilon. So if your particle is in epsilon energy state, your total energy is E minus epsilon of the remaining particles, and there are n minus 1 remaining particles. So the number of ways those move around, the multiplicity of the system without the first particle considering would be just this. And if your n1 is 0, basically your total energy, remaining energy of the n minus 1 particles is E, and you again have n minus 1 particles, and we had the probability of ni to be 1 by En. So all of these are constants, and there would be these many number of terms. So when you add up, you have 1 by gamma En times this.
Can I explain how probability of the n1 is the sum of
So the probability that n1 is in, suppose, 0 state is the probability that so suppose you have n1 in 0 and remaining in some state, and the remaining particles can be in any other state while keeping n1 to be at 0. So you have to, for finding the probability that n1 equal to 0, you have to sum over all the other states of other particles, so that your particle 1 can be in 0 state when the other particles are in many different states.
So and it's due to the constraint that total energy is E.
Not actually. This is basically if you remember in the probability thing, you have a total distribution function of fxy, and if you want the probability distribution of x, you integrate over y. So here you have a probability distribution of n1 and this probability distribution of n1, n2, n3, and so on. For finding the probability of n1, you sum over the probabilities of sum over all the states of the other particles.
So each probability is 1 by omega, and each value is that the numerator. Each probability is 1 by omega En, and there are these many terms in this sum. There are n terms, right? n minus 1 terms.
No, your n1 can be 0, 1, n2 can be 0, 1, n2 can be 0, 1, n3 can be 0, 1, and so on. So you can permute,
okay.
So your remaining n minus 1 particles can be in many different configurations while keeping your n1 constant. So you have to sum over all those configurations.
So sum over all those configurations.
Yes. And so P of n1 equal to 0 is basically and we have evaluated gamma of En, so we know gamma of En minus 1, and that is basically comes out to be 1 minus n1 by n. So your P of n1 equal to 1 is 1 minus this, which comes out to be n1 by n, which is kind of evident if you see that there are n1 particles over here, n0 particles in equilibrium. So probability that your system is in state with energy E is n1 by n and so on. So this is basically if you write in terms of temperature, you get. So this kind of gives a hint towards the next thing we would be heading to, which is the canonical ensemble, where your probabilities come out to be exponentials in the energies. So this gives a hint towards that. And you have the expression of E with E versus T. So you can always find various parameters such as the specific heat. You can find the specific heat of the system, which is just dET, which you can, I mean, if you differentiate this, then you will get some complicated expression. So this guy looks like this. The maxima happens at E by QD. And the initial curve looks asymptotically like this. And finally, it shows a power law decay of. So you have exponential rise initially and power law decay. This is the specific heat of the system. And also these probabilities are valid for when your T is negative. So you will still get these probabilities. So let's go to the next step in the lecture series, which is canonical ensemble. So we know in the microcanonical ensemble, your energy is fixed in the total system. And as a consequence, you get a equilibrium temperature, which is homogeneous all over the system. But we should treat both
energy and temperature in an equal footing, because both are you can control both of them, and they are thermodynamically in an equal footing. So in canonical ensemble, your temperature is specified and you determine your internal energy from this temperature. So you have a system which has a constant temperature T, and you have a reservoir which also has same temperature T, and you can have exchange of energy between these, and the system has a volume V. So there is input of heat allowed, but there is no input of work allowed. So no work is there in the system, and this reservoir of heat bath basically is considered to be very big, and the small heat exchange between the system and the surrounding or the reservoir does not change the temperature of the reservoir. So this is a NVT. So these are the quantities specified, and so this is a NVT ensemble. So let's denote this guy's microstate as μs, mu system, and this guy's microstate as mu reservoir. So your microstate can be the position and momenta of all the particles inside, or if your system is made of something different, you would have a different corresponding microstate. So let's just generically write that as μs and μr. So we need to find the probability rho of μs for the system. So for a given microstate, what is the probability of the system being in that microstate? Just like we did it for the microcanonical ensemble. So, but we know that the sum of systems, the sum of this system plus the reservoir, totally is a microcanonical ensemble because there's no energy going out of this. So the system R plus S, this is a microcanonical ensemble. And since your reservoir is like very large, the total energy of the system is greater than the energy of the total energy of the reservoir plus the system is greater than the energy of the system itself. So since the whole thing is a microcanonical ensemble, we can find the probability distribution of μs and μr at the same time, which is given by the microcanonical probability distribution. So that is rho μs and μr. And this is given by 1 by gamma s plus r. So your probability is 1 by gamma of the whole system plus reservoir, and times. So when your total energy is, if you have a microstate with total energy not equal to E total, your probability of finding that microstate is 0. So now what do we have to find? We have to find this direct. So how do you find this? So this is the probability that your system is in this microstate. And when your system is in this microstate, your reservoir can be in many microstates. So you need to sum over all the microstates of the reservoir of this probability to get the probability of your system. So this is basically sum over mu r rho of now once you have the mu s, you have h of mu s. So basically your since because of this condition, only those microstates of reservoir are possible where it's the energy of the reservoir is E total minus h of mu s. So you need to sum only over those states of the reservoir where your energy of the reservoir is this. And the number of these states is equal to gamma reservoir of E total minus is this fine to me. So number of states with number of states in the reservoir with this energy is basically this. Right? So now you have a sum over mu r, and your rho is constant over all these states. And like the previous example, we'll get a rho of mu s to be and this so this is like a constant, this quantity, because it does not depend on the system, and so this is proportional to exponential of 1 by kb the entropy of, so you can write this as like e power s by kb. So
What are we writing there?
yeah, because gamma r is equal, like kb log gamma is s, right? So this is the entropy of the reservoir. You need to put the entropy of the reservoir. It's the entropy of the reservoir at this energy of E total minus the energy of the system. And since your energy of the system is like very small compared to E total, you can do a Taylor expansion of S.
It's E power 1 by kV into entropy of reservoir at that point.
At that energy. E total minus H of yes. So let's write that clearly. Rho of mu s. And you can write S E total minus HS mu s as SR, sorry. Entropy of the reservoir. SR E total minus HS. Plus higher order terms. And since the entropy is small, the H of mu s is small, I'm neglecting these higher order terms. And if you see this del S, del SR, del ER, this is basically 1 by temperature of the reservoir. And we assume that the temperature is constant. So this is equal to the 1 by temperature of the system. So basically, this turns out to be SR E total minus right, and this is also a constant. So we can write rho of mu s to be proportional to exponential of minus Hs of
What does entropy of reservoir at total energy?
if your system has zero energy, then all the energy is in the reservoir, and the number of states in the reservoir for that total energy. So your rho of mu s comes out to be proportional to exponential of the negative of the Hamiltonian of S. And if you remember from the Liouville's theorem, that rho has to be a function of h of mu s for the system to be at equilibrium, and you see it is actually that. And so since rho is a probability distribution, you have to normalize it. So rho of mu s is basically 1 by z times e power minus h s mu s by kBT. And z is basically the sum over all the microstates. This is the normalizing factor, and this is the probability distribution. You have to keep in mind that this is the probability of finding the system at a given microstate, not the probability of finding the system at a given energy E. There can be many microstates with the same energy E, and sometimes people get confused that it's E power minus E basically, and so the energy of like energy 0 is most probable. Right. So this Z is called the partition function. The canonical partition. So now you have um, you have the probability density of probability of different microstates. Now you want to calculate various thermodynamic quantities. So for that, what do you do? So your average energy E would be basically equal to sum over mu s multiplied by the energy Hamiltonian of mu s and the probability of mu s, which is basically right. Now, if you look at this partition function, 1 by mu s, let's call 1 by kbt as beta. So, if you take a derivative of z with respect to beta, what do you get? You get sum over mu s, you get minus hs, h of mu s, and power minus. Right? So, if you see this expression and look at this expression, they're quite similar, right? So basically, your average energy E comes out to be minus 1 by Z del Z. Now you want to, so you can calculate the Helmholtz free energy, which is E minus Ts. And you know that F is equal to, F is a function of T and B. So S is basically just minus the F. This is I've written this as a total derivative because V is constant. So if you just substitute it here, you get E equal to and you can take you can write this in terms of beta. So T times df dt is equal to 1 by kb beta 2 minus kb beta square beta, beta, which is minus beta beta. So you get f is equal to e minus beta df d beta, and let me take this side. So e comes out to be um, beta df d beta plus f, and I can write this as a total derivative d beta of beta f minus. So what does this mean? Yeah, this gives beta. Yeah. So I can write this as a total derivative of beta f. And what we got here was E is, I should write this as H. Yeah. And this is equal to minus 1 by Z.
That is H of reservoir or system.
Our system. Now we're just considering the system. So this is d beta of Z, and you can write this as minus of d beta of log Z, right? And so comparing this and this, you get beta f is equal to minus log Z. So f is equal to minus 1 by beta log Z. So once you're given so what is your task? You have the probability distribution. Now you have to somehow compute the partition function. And once you're given the partition function using this simple relation, you get the Helmholtz free energy. And from Helmholtz free energy, you get the entropy. And using this relation, you can get your internal energy. So finding out the partition function is the most. If you are able to find out the partition function, then your problem is basically solved. So you get all your thermodynamic it just depends on the partition function. And yeah, so is this a good time to stop? Yeah, I've done all the, I can give examples. I need to give just examples. I have not prepared examples.
How did we equate that to minus 1 by Z?
This is E, right?
Ah.
E is minus 1 by Z.
Okay, we just. So E is the ensemble area of X.
Yeah. Okay, I should also say that so this is like your system and there is a reservoir. And in our while we did the microcanonical ensemble, we show that when you have a total microcanonical ensemble, your system and reservoir has basically it has this single energy E where it is most probable, and that energy is where the gamma was the product of gammas was maximized, and other energies were exponentially less probable. So whatever this average energy E H you calculate, that turns out to be this energy where it's maximized, and your system would be most probably found in this energy. Though your system can exchange energy with the surroundings, your system will be found at that at this energy which is given by this quantity. And and other energies are exponentially less probable. What else can I say? Oh, I should also say this that I had once told you about moments and so on, right? So you can find moments of h of s by taking many derivatives. If you take second derivative of z with beta, you will get basically a hs square term and a term with just hs. So using that, you can find the moments of E of H basically, and you can calculate the variance of H, which is basically H square minus, and this quantity you can show will become exponentially less as you move away from the average energy. I can do the classical test. I mean, I have to do it from my mind. I can
write what to do. What do you like when we move away from the average energy? The H variance reduces exponentially.
Oh wait. Sorry. As your n tends to infinity, this becomes very sharply peaked. I mean, this guy reduces.
The number of states would be like some Gaussian, right?
Yeah.
So away from the peak, it would be big.
So okay. I should also say one more thing. What is the probability distribution of the energy? Rho of E. Basically, you sum over all the microstates with energy E. Mu s such that H of rho of mu s. So this would come out to be basically a sum over the energies. Sorry. Okay, so this would basically come out to be a function which is called the density of states multiplied by the probability distribution e power minus beta h mu s, or you can say e. So this is basically the number of states with energy E. All the states with energy E have equal probability, right? And if you're summing over all the states with energy E, you basically get this omega E, which is the number of states with energy E.
Is it gamma?
No. Gamma was the number of states between E and E plus delta, right? and if you divide that by the you get the density of states. Here, so what is the number of states lying between E and E plus delta? That is gamma of E, which is omega E dE, right? And omega E dE times this probability would be the probability that your energy lies between the range E and E plus D. So your probability density of energy E would be basically the density of states times the probability E, this exponential minus beta E. And this omega E basically it increases with E. And this guy exponentially decreases with E. And this total function shows that there is some peak. There would be some peak, and this peak would, wherever this peak is, that peak would tend to the average energy as your n increases, and this width is if you calculate from the variance of this probability distribution of E, that would tend to 0 as n increases.
What does it signify when n tends to infinity? The energy of almost all the particles is equal.
Energy of the system is taking a single value. It is not fluctuating that much. So, if you have a small system like a small protein or something, the protein is in a solution which is like a bath. And the solution can, since there's a less number of proteins, it can take a small energy and it will disturb the system by a lot more. And so your energy will be fluctuating about a large amount compared to, because your energy is small, the fluctuation would be, the ratio of the fluctuation to the energy would be like large. But if you have a large system, your energy would tend to fluctuate lesser, and this guy would become more sharply peaked as you increase energy. And do you want the classical ideal gas in this ensemble? Grand canonical or quantum stack?